Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 25th, 2025, just 2 days ago. It introduces a deterministic, prime number-based feature mapping that can both preserve geometric structure for reconstruction and act as a high-entropy hash, while beating normalized Gaussian random projections with roughly a 0.5% drop in off-diagonal error and about a 2% tighter overall error surface. The paper is titled Primal, a unified deterministic framework for quasi-orthogonal hashing and manifold learning. And, as we will see later, the implications for how we design projection layers and privacy-preserving representations are quite significant. Alright, after that high-level pitch, Table 1 lays out the core symbols that drive the prime-based encoder. The table distinguishes the input dimension d, the output embedding dimension d, and its half k, which is important because the method pairs cosine and sine features. It also defines x as the raw input vector and z as the projected latent representation. Finally, sigma appears as the single scaling knob, and w is the prime constructed frequency basis that replaces random Gaussian weights. Well, Table 2 compares how expensive each projection is in time and memory. The table shows that normalized random Gaussian and dynamic prime both need initialization and forward passes on the order of d times d and n times d times d. Dynamic prime then supports an inverse mapping with cost on the order of n times d, assuming the pseudo-inverse is cached. Static prime is much lighter, with initialization on the order of d, forward cost on the order of n times d, and space only on the order of d. Alright, the previous table quantified computational cost, and Figure 1 now shows what that buys in terms of geometry. The top row compares cosine similarity landscapes. The Gaussian baseline spreads mass away from zero, while static prime concentrates a thin ridge at zero similarity, so pairwise codes collide less often. The bottom row plots root means square error over dimensions and sequence lengths, where static prime consistently yields about 2% lower global interference than the random Gaussian codebook. So, while Figure 1 focused on average interference, Figure 2 digs into worst-case behavior relative to the Welch bound. The left panel shows optimality ratios, where static prime in cyan clusters tightly just a few times above the bound, while the Gaussian baseline in red spreads out toward ratios near 5. The right panel plots excess coherence, which measures how far the most correlated pair deviates from ideal, and static prime again hugs low values around 0.2, while Gaussian mass extends toward 0.6 and beyond. Alright. Figure 3 contrasts how dynamic prime behaves as either a manifold learner or an orthogonal hash. The left block of columns shows the low frequency setting, where spirals and circles become neatly unrolled in latent space and reconstruct almost perfectly, so topology is preserved. The middle columns depict a high frequency, very low dimensional hash that scrambles structure and makes reconstruction fail. The right block increases dimensionality, which restores a spherical, quasi-orthogonal cloud that is ideal for hyperdimensional computing style operations. So the big message is that a simple, deterministic, prime-based encoder can replace random projections, giving tighter quasi-orthogonality while offering a single knob that moves smoothly between precise manifold learning and strong cryptographic style hashing. This could reshape how we design both compression and privacy layers. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.